Hey everybody, my name is Ben Mader and I'm a hydraulic engineer with Alden Research Laboratory. Our contact info is down here in the bottom left. My talk today is called CFD as a tool for nature-like fishway design, a case study. So CFD, computational fluid dynamics, is a computer modeling tool that's often used within the realm of fish protection and passage. Here's an example here. This is a flume that empties into a conduit. And there's a fish lift that goes up and dumps water and fish into this flume. And then we see the water go down the conduit and eventually up into the head pond. So this is a very typical application of CFD in fish passage. You can see it's we're talking on the order of tens of feet here for the domain size. Relatively simple geometry, a very kind of bread and butter type application for CFD. It's often used as an analytical tool as well as an iterative tool in this context. Other applications in fish passage include looking at near field dynamics and tail races of hydropower dams, for example. Here we have a fishway entrance and we're looking at velocity cross sections right next to these turbine discharges. Us also looking at even smaller scales down to the scale of intake screens, for example, where we're looking at dynamics at the pore scale with regard to smaller life stages. So again, these are typically characterized, these applications, by regular geometry in small domains. We usually look at engineered structures such as fishways, intake units, exclusion screens, etc. But what about non-traditional type applications? For example, nature-like fishways. Nature-like fishways are relatively new to the scene of fish passage, and the idea is to kind of create something nature-like. So lots of variability in the flow, large roughness elements. We can see there's lots of rapidly varied flow. These domains are relatively large. There's a lot of uncertainty in how these things behave and how best to design them. So numerical modeling might be a good way to reduce the uncertainty in nature-like fishway design. However, these designs are often, and the flows are often too complex for simple depth average kind of shallow water 2D models. So maybe 3D CFD might be warranted in some applications as a design tool. But as I said, there's prohibitively large domains often that need to be considered. These kind of reach scale domains are not typical for very highly resolved CFD models. So I want to talk about a case study in which we did use CFD to design a nature-like fishway at Saccarappa Falls in Westbrook, Maine on the Presumpscott River. So the owner of this project was Sappi, a paper company with roots in Westbrook going back to the 1850s as a paper mill. The Saccarappa site is characterized by two channels splitting around an island. And there's a spillway dam over each channel and a old hydropower powerhouse down here. So if Sappi is going to surrender their FERC license and remove the dams, remove the infrastructure, and provide fish passage through the site. We have both the upper falls here in these channels and the lower falls down here in Saccarappa. So the concept was to take out the spillways in the eastern and western channel, remove the old powerhouse, put a double Denil fish flatter around the lower falls within the old tail race, and that was done by the local firm Acheron Engineering, and then put two nature-like fishways through the upper falls in both the channels, and that was done by Alden, the design and modeling. So here's some shots of the site. These are the lower falls to give you an idea of the vertical scale going on here. So lots of rough bedrock, quite a bit of drop over these features. This picture is at high flow, so the kayaker is having some fun down there. Here's a shot of the western channel. Lots of bedrock roughness. This is strongly foliated, dipping gneiss. Here's a look at the eastern channel. You get an idea of the roughness looking at the tripod out here, so very rough. The idea was to sculpt this bedrock into nature-like channels for fish passage. So the design objectives were to provide continuous migration corridors at several different flow rates, while minimizing lowering of the head pond for upstream water usage, minimizing bedrock excavation. This all had to be hoe rammed out because it was in a residential neighborhood, so no blasting, while emulating a natural bedrock channel to make it nature-like, preserving aesthetics, and minimizing hazards to boaters and fishermen. So this was the final design morphology that we came up with at Alden. Here's the eastern channel again and the western channel, and we can see multiple subchannels, lots of variability, some meandering, kind of characteristic, reminiscent of bedrock type morphology. So the idea was lots of morphologic variation to give the fish lots of hydraulic options for getting up this thing. So resting pools, dissipation pools, step pools, more kind of plain bed features. So lots of variability. So how did we get there? Well, we used CFD modeling, as I said, but there's two main challenges with that. One was the roughness. So how do we model this roughness in a manageable way? With CFD, we're lucky to we have the vertical resolution, so we can pick up a lot of those roughness features that cause form drag, and we can explicitly model that kind of, foot to 2 foot scale ups and downs of the bed that we think is going to exist after construction. And in explicitly resolving those elements, we limit the emphasis and the need to use kind of a black box approach of a skin drag type Manning's in or roughness link scale in the CFD model. So we want to really explicitly model as much of those roughness elements as we practically can. Of course, we end up with a bunch of grid cells when we do that, which becomes very awkward. So what we ended up doing was doing a hybrid approach, where part of the domain is in 2D and part of it's in 3D. The second challenge was, how do we synthesize this roughness? We don't have the proposed surface surveyed. There is no proposed surface yet. So we had to somehow synthetically roughen the surface in CAD. We start off with kind of 1 foot contours that create a smooth surface, and then we synthetically texturize that. So challenge one, modeling the roughness in CFD. So we had to, because the roughness is so fine scale, we have a large domain here that's essentially the 2D shallow water mesh block, and into that we drop these high resolution 3D mesh blocks that picks up that fine scale roughness explicitly. And this is a practical approach that's made possible by our modeling software, Flow3D by Flow Science. It's a really cool feature of Flow3D. Here's another view of the domain. We can see the increased resolution within the 3D mesh blocks in both the eastern and the western channel. Here's another shot zoomed in of a 3D mesh block to give you an idea of vertical resolution here, about 1/4 foot in the vertical. So how do we synthesize that roughness? What do we think this bedrock's going to break up like? We can see it's pretty variable, and we want that as part of the design. Well, we had a laser scan image of this bedrock here that we then sampled, and we normalized those elevations about 0 to get our kind of representative patch of roughness here. That we then took that patch of roughness, tessellated it so that we'd have a texture to drape over our proposed surface for modeling. So here's our relatively smooth proposed surface built from 1 foot contours in CAD. We drape that patch roughness over top. And then we map our surface onto that roughness to give kind of a synthetically roughened proposed surface with what we think the bedrock's going to break up like, so that we can explicitly model those rough net form drag in the 3D mesh block. Again, this is a plan view of one of the subchannels in the western channel. You can see it's pretty smooth after we build it from the 1 foot contours, and then we synthetically texture it here. So that's not exactly what the channel is going to look like, of course, but it gives us a characteristic roughness to model. So our design approach, as I said, we use 2D as well as 3D, but the really kind of workhorse for the iterations was the 2D model only, without the 3D mesh blocks. So that's really how we went around here and did our iterative design. Once we got something we like, we texturized it in CAD. We dropped in our 3D mesh blocks, did our hybrid model, ran our fish survivorship model to look at passage likelihood, and then we iterated as necessary back into our 2D loop here. Once we got something that we liked, And that, of course, was our final design that we took to construction. So here's some CFD renderings of the western channel: low, moderate, moderate, and high flow. The eastern channel a little wider and shallower. You can see the comes into play more at the higher flows. And the advantage of 3D, so this is one of the 3D mesh block here, is we pick up the vertical variation too. And we can see the black contour is 6 feet per second. So we're dealing mostly with, not Atlantic salmon so much here as, some of our weaker swimmers, American shad, river herring. And we want to look at that 6 feet per second threshold. And so we can see there's lots of marginal area outside that black contour that's available for the fish. And we can see that that's mostly thanks to all that roughness. And we can see it in the 3D rendering, in the 3D model, and the high flow here. That's all great, but can it be built? This is a really complex design. It's more art than anything, very non-traditional. So we had to come up with construction plans to bid on. And we did the traditional approach of having lots of alignments and cross sections all over the place to try to capture this design. One of the things we really wanted to focus on was hydraulic control points, that we wanted to make sure the contractor kept those within a tighter tolerance to maintain the hydraulic grade line through here and maintain our pools. So Sumco Environmental was our contractor on this, and they got underway. They took out the spillways, this is in the Western Channel, and started hoe ramming. Lots of excavators involved here, lots of hoe ramming. One of their prime tools to implement the design was real-time GPS rather than those traditional cross sections. It turns out the bedrock didn't break up like we thought it was going to. Here's one of the sub-channels in the Western Channel, and it broke up actually quite smooth. This is what we were targeting, this is what we got. So the contractor went back in and added, the texture that we wanted. So we can here's the texturized channel here. Here's it with some flow on it. This is a pretty low flow. You see some variability in the flow down through there. It's not just a supercritical flume. Here it is a higher flow. We got this turn down here that's providing backwater on this channel to reduce the velocities. Here's the as-built surface for the Western Channel. So we can see the sub-channel here that's a little more sinuous, and here is kind of a higher volume, higher flow rate channel, so lots of options and variability for the fish. Here's a shot of the Eastern Channel as built. There's no water on it right now, so I had to sketch in the sub-channels here. But again, lots of variability. So it turns out that this can be built if you have a good contractor. We went out and as-built surveyed the Eastern Channel, shown here. This is the design without the texturing, and this is what was actually built. And so it's pretty cool to flip back and forth between these two. You can see the texture added to the Eastern Channel by the contractor, and pretty darn good adherence to the contours and features that we wanted. There's a lot of working with the native bedrock to try to get this to happen, and they did a pretty good job of doing that. So in conclusion, this hybrid 2D, 3D CFD approach does indeed seem to be a promising tool for coming up with complex nature-like fishway designs. Modeling roughness is a challenge. Explicit resolution of the roughness elements limits uncertainty in the modeling. We have to rely less on a kind of roughness link scale or Manning's N-type black box approach if we can actually model the form drag elements. Lessons learned. So the takeaways here: 2D simulation is really best for quick iterations. They're simple, but they're quick. And then the 3D is great for intermittent checks, less frequently. In doing CFD modeling, it allows us for more freedom and less uncertainty in nature-like fishway design, which is better for all. And it allows complex designs to be possible. So construction of these complex designs we've seen is possible, so long as you have real-time GPS and a good contractor. So a quality contractor will allow you to try something new. And of course, good clients like Sappi make cool, new, novel things like this possible. So thanks everyone for tuning in. Have a great conference.